In this video, we're going to continue talking about dienes, and I actually want to first look back at something we covered in the previous video, so in the dienes 1 video, when we were looking at 1,3-butadiene. And we said in this molecule, each carbon is sp2 hybridized, so each carbon has an unhybridized p orbital. And on the left side, over here, we drew that structure with the unhybridized p orbitals. And those are atomic orbitals. Each atom, each carbon atom, provides one of those unhybridized p orbitals. Then when we said in reality, the p orbitals are overlapping, we drew this molecule on the right with the overlapping p orbitals. And what we drew here is actually a molecular orbital. So when we talk about atomic orbitals overlapping and forming new orbitals, that's a molecular orbital. This is one of the possible molecular orbitals for 1,3-butadiene. So in this video, we'll draw all of the possible molecular orbitals for 1,3-butadiene. So more on MOs, or molecular orbitals. And let's look again, we're looking at 1,3-butadiene. We'll draw on an energy scale. I'm going to start with just that same structure with the individual p orbitals on the left side. And then on the right side, we'll draw the molecular orbitals. So each carbon atom has an unhybridized p orbital. That is an atomic orbital. So we have 2p atomic orbitals. Atomic orbitals you can abbreviate as AOs. So all 2p atomic orbitals, they're all in the same plane. These all have the same energy. So as we're talking on an energy scale, we have 4 2p atomic orbitals, and they're all at the same energy. So we have 2p AOs here. And that aligns with the structure we've drawn here on the left. Now thinking about the number of electrons in the p orbitals might be helpful to look back at the skeletal structure. So I'll highlight that in green here. Now we're only thinking about the electrons in p orbitals. And if we have 2 double bonds, there are 2 electrons per double bond. So that means we have 4 total electrons in the p orbitals that are part of double bonds. So if we have 4 2p atomic orbitals that are the same energy, then we put 1 electron in each atomic orbital. Now we have our atomic orbitals, all the information we need set up on the energy scale. We can show how we combine those to form the molecular orbitals. In the molecular orbital picture that we drew previously, so this one, which I will be copying over, I'll just go ahead and do that now. And you can redraw this in your notes. This picture, this representation has the lowest energy of all of the possible molecular orbitals. That's because we have the best overlap of the p orbitals. Another way to represent this is a little bit simpler, so I'll just go ahead and scoot that over, where we just have 4 p orbitals overlapping the same phase on either side. So we have all blue on top, all green on the bottom. And this is essentially the same thing that we are representing, right, with that structure where we drew in the carbons and hydrogens. So this we'll call the pi 1 molecular orbital. The lowest energy, has the best overlap. One thing that it does have is a node, and that is an area where no electrons can exist. There is one node that just goes across the center. And that's always going to be present in any p orbital. There's a node across the center of the p orbital. So we have one node. Now, as you increase in number of nodes, you increase in the energy of the molecular orbitals. And so as we add and draw the additional molecular orbitals, they will increase in the number of nodes that are present. A couple of things to remember from our previous videos on molecular orbitals. The number of atomic orbitals that you start with should be the same number of molecular orbitals that you end with. We start with 4 atomic orbitals, so we should have 4 molecular orbitals. We also know that whenever we form a bonding molecular orbital, we also form an antibonding molecular orbital. So for these 4 2p atomic orbitals, we will form 4 molecular orbitals. 2 of them will be bonding and 2 will be antibonding. So I'll just draw those along the energy scale now. So we have pi 1. Pi 2 will be slightly higher energy than pi 1, but still lower energy than the atomic orbitals. Pi 3 is now an antibonding orbital. And pi 4 is the highest energy antibonding orbital. So all of these are the MOs. Okay, so we have one node in the pi 1 molecular orbital. The pi 2 molecular orbital will have 2 nodes, and that occurs by keeping the p orbitals in the same phase on the left, and then switching phases for the 2p orbitals on the right. So now we have an additional node right through the center here where we can't have any overlap. So here we have 2 nodes, slightly higher energy for pi 2. Pi 3 is even higher energy. We will now have 3 nodes present, and that occurs when we have the 2 p orbitals in the center overlap with each other, but do not overlap with the p orbitals on the outside. So we have the same node through the center horizontal, and then we have an additional node here and an additional node here. So in this pi 3, we have 3 nodes. So that's even higher energy than pi 2. And then in pi 4, we'll have 4 nodes, and that's where for each p orbital across the linear molecule, the phases are flipped. So if our first p orbital for carbon 1 looks like this, then our p orbital for carbon 2 will be opposite phases. P orbital for carbon 3 will be the opposite phase. And p orbital for carbon 4 will be the opposite phase relative to the carbon adjacent to it. So now we have the horizontal node through the center, and then we have 3 additional nodes. So here we have the 4 possible molecular orbitals for 1,3-butadiene if we're only focused on the 2p atomic orbitals. The last thing we would do here is fill in where electrons are present in the molecular orbitals. We start with 4 electrons in atomic orbitals, and we know that because there's 2 double bonds, 2 pi bonds, so 2 electrons per bond, that's 4 electrons total. We will fill molecular orbitals from lowest energy to highest energy first, and electrons in the same orbital cannot have the same spin, so we put 2 electrons in pi 1, one represented with spin up, one represented with spin down, and then 2 electrons in pi 2, one represented as spin up and one represented as spin down. So this here, let's use a different color now, where we show the 4 pi molecular orbitals and the electrons filled in pi 1 and pi 2. This is the molecular orbital diagram representing 1,3-butadiene. So just like we were discussing when we were talking about the more simpler molecular orbitals, these diagrams in molecular orbital theory really helps us understand where electrons are located within a molecule. So the pi electrons, at least 2 of the pi electrons, are delocalized across all 4 carbons. And we can see that from this molecular orbital here, where all of the p orbitals are overlapping. There are also some electrons present in the higher energy pi 2 molecular orbital. This also tells us that if this molecule were to give up or donate electrons in a chemical reaction, it would donate electrons from this pi 2 molecular orbital. And if it were to accept any electrons, it would accept electrons into the pi 3 higher energy antibonding orbital. So again, helps us understand where electrons are located in the molecule. I have an image down here. I don't expect you to be redrawing this in your notes, but this just shows the electron density in this molecule, where the red color represents higher electron density. And in this electrostatic potential map, we can see that the high density of electrons, so the red color, is shared across that carbon-to-carbon single bond. This is where that single bond is. Then we have double bond and double bond, and so that electron density is shared across that double bond, and that aligns with this lower energy molecular orbital here.